This lecture discusses chi-square goodness of fit test. The FBI classified violent crimes in 2010. A simple random sample of 500 violent crime reports from last year yielded the frequency distribution below. Has the last year's distribution of violent crimes changed from the 2010 distribution? This hypothesis test is quite different from the hypothesis test we discussed before. In the past, we were interested in only one parameter, but here we want to compare the whole distribution. The null hypothesis is that last year's violent crime distribution is the same as the 2010 distribution. The alternative hypothesis is that last year's violent crime distribution is different from 2010 distribution. Notice that an alternative hypothesis usually contains words such as different, and the null hypothesis contains words such as same. The logic of the test is to compare what we observed with what we expect in the null hypothesis. Let's consider a simple example. For a balanced die, we may get any number with probability 1 over 6. If we toss a balanced die 600 times, we expect to get 100 ones, 100 twos, up to 106. If the observed frequencies are quite different from 100, we may suspect that this die is not balanced. We use the same reasoning for this problem. Let's introduce some concepts. Observed frequencies are the actual frequencies observed in the data. Expected frequencies are the frequencies expected when the null hypothesis is true. In the example of dice, the expected frequencies are 100 because we expect 100 times out of 600 tosses for a balanced die. The observed frequencies are the actual counts when you toss the die 600 times. More generally, we calculate the expected frequency for each possible value of the variable using n times p, where n is the sample size and p is the relative frequency or probability given for the value in the null hypothesis. This table shows the details of calculation. The variable has 4 different values, so there are essentially 4 categories, namely murder, rape, robbery, and assault. The observed frequencies are the numbers given in the problem. For example, the observed frequency for murder is 3. To get the expected frequency, we use 500 times 0.012, where 500 is the sample size and 0.012 is the probability of murder based on the 2010 distribution. Similarly, we can calculate the expected frequencies for the remaining categories. Just use 500 times the corresponding probability. If observed frequencies are close to expected frequencies, the null hypothesis may be true. That is, last year's violent crime distribution is the same as the 2010 distribution. If observed frequencies are quite different from expected frequencies, the null hypothesis may not be true. That is, last year's violent crime distribution is different from the 2010 distribution. How to judge whether observed frequencies are different from expected frequencies? We may calculate their difference. Because the difference can be positive and can be negative, we square them. Their sum can serve as a measure about how close observed frequencies are to the expected frequencies. The test statistic can be expressed in this way. The sum of O minus E squared divided by E, where O means the observed frequencies and E means the expected frequencies. This test statistic approximately follows a chi-square distribution if the null hypothesis is true. The number of degrees of freedom is 1 less than the number of possible values for the variable under consideration. The goodness of fit test is used to check whether the distribution of frequencies is consistent with a given distribution. There are some assumptions. First, all expected frequencies are 1 or larger. At most 20% of the expected frequencies are less than 5. These two assumptions are needed to guarantee that the test statistic approximately follows the chi-square distribution. We also assume simple random sample. To perform a hypothesis test for the distribution of a variable, we first need to identify null and alternative hypotheses. They are fixed. The null hypothesis is the variable has the specific distribution, and the alternative hypothesis is the variable does not have the specified distribution. Next, we need to decide on the significance level alpha. Usually, alpha equals 0.05. Occasionally, alpha equals 0.1 and 0.01. Then, we need to compute the value of the test statistic. Denote the test statistic as chi-square 0. It is the sum of O minus E square divided by E, where O and E represent observed and expected frequencies. We can draw a conclusion using either the critical value approach or p-value approach. First, make sure that the degrees of freedom is c-1, where c is the number of possible values for the variable. We can use a chi-square table to find the critical value. The rejection region is always larger than the critical value. If the test statistic is larger than the critical value, we reject H0. Otherwise, do not reject H0. When using the p-value approach, the p-value is the probability larger than the test statistic. The degrees of freedom is c-1, where c is the number of possible values for the variable. If the p-value is less than the significance level alpha, we reject H0. Otherwise, do not reject H0. Last, make sure to interpret the result of the hypothesis test. In the example of violent crimes, at the 5% significance level, do the data provide sufficient evidence to conclude that last year's violent crime distribution is different from the 2010 distribution? We have already calculated that the test statistic is 6.529. Notice that C equals 4 because the variable has 4 possible categories. The significance level is alpha equals 0.05, and the degrees of freedom is c-1 equals 3. Using the critical value approach, the critical value is chi-square 0.05. We can find its value using a chi-square table. It is 7.815. The test statistic is less than 7.815. It does not fall in the rejection region. Therefore, we do not reject H0. When using the p-value approach, the p-value is 0.089. We can calculate it using Excel. It is 1 minus chi-square dot dist 6.529, 3, and 2. The p-value is larger than the significance level alpha. We do not reject H0. Both approaches lead to the same conclusion. At the 5% significance level, the data do not provide sufficient evidence to conclude that last year's violent crime distribution differs from the 2010 distribution.